Hi, calculus students. We have explored all of the different tests for always positive series and alternating series. So I just wanted to give you a toolkit here so you could work through them on your own. So where do we always start? We always start with the nth term test. Do the terms of the sequence go to 0? If not, diverges, done. If they do go to 0, then we look for our favorite kinds of series, geometric series or telescoping series. Remember that on the AP exam, the only kind of series where you actually need to find a sum are either geometric or telescoping. So that's a big clue to you. If you're actually asked to find the sum of a series, then you know it's either going to be geometric or telescoping. Then we have our favorite kind of series, which is a p series. 1 over n to the p. If p is greater than 1, it converges. If is 1 or smaller, it diverges. Remember, when p is 1, that is our harmonic series. We see that harmonic series and we immediately know diverges, done. And what happens most often is that the series is almost a series we know. So it's almost a geometric series or it's almost a p series, but not quite. So we look for first direct comparison. So is the series that we're looking at bigger than a series that we know diverges? If it's bigger than one that diverges, it's even divergier, so it diverges as well. If the series we're looking at is smaller than a series that converges, remember, these terms are going to 0. So if our series is penned in between something that goes to 0 and something that converges, our series also converges. So by direct comparison, if you're bigger than something that diverges or smaller than something that converges, you can use direct comparison. Obviously, that doesn't always work. So then we go to limit comparison. If the limit of the ratio of the two series is any finite number, remember, for a limit to exist, it has to be a finite number. So if the limit of the ratio exists, then it definitely converges, or it does the same thing. So if you compare it to something that converges, yours also converges. If you compare it to something that diverges, it also diverges. A great example of these is if I'm looking at direct comparison, I know that the sum of 1 over n diverges. So I also know that the sum of 3 over n diverges because 3 over n is always bigger than 1 over n. It's bigger than something that diverges. But if I'm looking at something like 1 over 2 to the n, 1 over 2n, then I'm smaller than something that diverges, which doesn't help me. And then I have to go here to that limit comparison test. And then, wah wah, plan Z. If none of these work, you have to use the integral test. If the terms are decreasing positive and they're going to 0, then you have to, if the improper integral diverges, your series diverges. If the improper integral converges, your series also converges. Do they converge to the same thing? No. Then we get into our alternating series. And in order to prove that an alternating series converges, all we have to show that the terms go to 0, done. Which means that something like our alternating harmonic series is going to converge. Does our harmonic series converge? Definitely not. So that gives us to right here, converging absolutely versus converging conditionally. So if a series converges when it's alternating, but diverges when it's not alternating, we say it converges conditionally. It is a lot easier to show that an alternating series converges because all you have to do is show the terms go to 0. In order for a non-alternating series to converge, they have to go to 0, and it has to happen quickly, very, very quickly. So something like the harmonic series, the terms go to 0, but they don't go to 0 fast enough, so it does not converge. So once we look at an alternating series and we show that the alternating series converges, then we have to decide whether the non-alternating series also converges. And once you remove that alternating piece, that takes you back to those previous slides where you look at, is it a p series? Is it geometric? Is it something we recognize? And then we have these wonderful tests. We have the ratio test, the nth root test, and one that I TBD. So the ratio test says that the ratio of the next term to the previous term is getting smaller. Remember, if it's between 0 and 1, then they converge absolutely, which is great. You don't have to worry about conditional convergence. This is actually going to be our favorite test when we're creating our own power series. And then we have the nth root test. If you have something to the nth, a rad n, or if you can take it out, that's a really easy test, and it's also really obvious when you should use it. So the next step, now that we can decide if a series that we have been given converges or diverges, the next step is to construct our own series. And we are going to look at what intervals does a series converge. It might converge, every series is going to converge at its center, but how far away can we get from the center and still have that series converge?